Good afternoon, everybody. Welcome to another wonderful afternoon of organic chemistry, Chem 170, with your host, me, Dr. White. As you know, I finished grading test number 3. I posted the scores in Black Run School D2L, and I also sent each of you an individual email with the points on each problem. And therefore, what we're going to do today is I'm going to be going through test number 3 answers. By the way, all of you did good. Thank you. And I really appreciate that. And I'll go through that. Then I have a special surprise for you, really. And next, I will continue with carbohydrates. All right, let's get going. Remember, on my test, if I make a mistake, why, if I were in your shoes, I'd have a question. What grade am I getting now in your class? That's a good question. Let's find out. This is assuming you've handed in all your labs. And those of you who have, just about everybody, you can see I'm not a hard grader. So we're going to forget about the labs for now. And this usually is quite valid, assuming you handed in all your labs. All right, method 1. Take the sum of your 3 test scores divided by 300, you get X. 90 and above is an A, and this point breakdown letter grade is in my syllabus. Anyways, 90% 90 and above is an A, 80 89 B, 70 79 C. I don't think I have anybody below that level at all. Thank you. All right, that's method 1. But remember, the lowest test score to 4 tests is drop. So there's a second method you can also try to give you a heads up or indication what grade are you getting at this current time. All right, second method is take the sum of your 2 highest test scores and divide by 200. If you get a Y and the number is 90 and above, you're now getting an A, 80 89 B, 70 79 C. And like I said, I don't have anybody lower than that. I'm not sure if I even have anybody in the 70s. But anyways, that's it. Any questions about how to determine your current grade? We still have lots of points. We have test number 4, 100 points, and the final exam, are you ready for this? 200 points. So we've got a lot to go yet, and you can still get a very good grade. All of you. Now, I'm going to need some help. Give me a thumbs up. Did I teach you already how to clean a bathtub using Barkeeper's Friend? Yes, I thought so. Thank you. All right. It's time for a special surprise and gift from me, Dr. White. And let's go to Blackboard. Wrong school, D2L. All right, everybody see D2L on your screen? Thumbs up, people. Thank you. We're going to click on assignments. And you'll see, oh no, look, extra credit project. And let me switch to view. Extra credit project, what's that? Well, let's open it up and find out. All right, everybody see the extra credit project on your screen? Thumbs up, people. Thank you. Let me make it a little bigger. All right, extra credit project, 10. Hold on, I gotta do this fancy way. Extra credit project, 10 bonus points. It's like getting 10 more points than any one of your tests or your test total. How do you get 10 points? Create a chart that contains 10 organic molecules that are found in the ingredient list of commercially available products. In other words, anything you can buy. And you can use a molecule only once in the chart. And also you can get up to 3 molecules per product. That's my sneaky way of having you look at a couple different things, ingredient list, to get full credit for that molecule. All entries in a row must be correct. For each entry, record the name of the product, the name of the molecule, and one functional group, or the only functional group. If there's more than one functional group in a molecule, you only have to name one. And in that molecule, don't forget to put your name on the chart. All right, the following illustrates how it should look. For those who know how to make a table, if not, see me during my office hours. I can show you on Word. And you have a table, first column product, next molecule, last one functional group. And if you had brand X wine, like Boonesbury, boy, when I was in college, that was the cheapest wine you could buy. And we did. Anyways, and in there, there's ethanol, and that's an alcohol. Now, to make this interesting, there's certain molecules you cannot use. You cannot use sucrose, ethanol, isopropyl alcohol, acetone, ethyl acetate, propane, acetic acid, or methane. There's certain products you can't use. Beer, wine, vegetable oil, vinegar, gasoline, propane gas, natural gas, orange juice, milk, sugar, butter. Everything else is fair game. All right, this is important. Ingredients must appear on an ingredient list on the product, and they must contain a functional group discussed in this class. There are a number of functional groups I didn't talk about in this class. I only got one semester, 17 weeks approximately. So I have to include the important ones for your daily life, but not all of them. Now, from the lab and the test number 3, you know there's certain esters like in a banana. Well, you can't put down banana, what is it, isopentyl acetate, and it's an ester, because I've never seen a banana that I could buy. I don't like bananas, honestly, but I never saw a banana with an ingredient list. What chemicals are in it? It doesn't exist. All right, now, this is important. It's due by the end of the day, May 5th. And if I did this correctly, May 5th is the day after test number 4. So you got plenty of time. No late projects accepted. Please upload it as a PDF file or MS Word file. Now, this is important. This is an optional project. You don't have to do it. But if you get it right, you'll get 10, 5 and 5, 10 bonus points, which never hurts anybody's grade, usually helps it quite nicely. All right, now, important thing. Beware, not all names on labels are UPAC or common names. Simethicone, OL ending, ONE ending. Ketone, no, it's a silicone compound. Now you can use Google or ask me to check your structures. You can use Google, look it up. And to use Google, if you haven't done it already, place the name of the chemical you're looking for, the structure, and then the phrase chemical structure. And one of the first couple hits in the search will be that structure. So all you got to do is 10 molecules, all different, 3 from each product. So you got to look at 4 different products and put down the functional group. Now, it's happened some years where students think, oh, everyone has to be different functional group. No, they could all be alcohols, they could be ketones, they could be esters, carboxylic acids, all of them, or a mixture. It's up to you. Now, let me show you how easy it is.
So I have a question, Dr. White. So, from what I understood, what you said, so all you want us to look out for is processed food or items.
No, anything you buy that has a ingredient list on it with chemicals, organic chemicals. Let me show you something. Everybody see this? Carmex. And if you looked on the ingredients label here, which you probably can't see, one of them is phenol. So you could put down one of the entries, and this is not a food. I hope not. I don't know, maybe you eat it, I don't. Ugh. But anyways, Carmex, phenol, and it's got 2 different functional groups. You could put down alcohol or aromatic ring, either one, and you get your 1 point. I just gave you a free point. Carmex, phenol, alcohol. And there are 2 more you can get from here if you got any. Now, you don't have to buy the product. When I first started doing this extra credit, I haven't done it in a while, but I know it's easy. I go into any supermarket or big box store and either go into the personal care area or go into the food area, the grocery store area. And I just pick up things, and just like that, you can get 10 different molecules and 4 different products within minutes. If you're really lazy, you can go in the store and with your cell phone photograph ingredients list, or just go down to your refrigerator and go into your bathroom, and you can find a whole lot of things.
Dr. White, do we need to draw the structure as well?
Nope.
Okay.
Nope. If you want, I'm not going to stop you from having fun. Now you know I'm an organic chemist. He thinks it's fun to draw structures, and it is. All right, do you see the chart? Example table? All you have to do is have 3 columns. First column, product, and you put in the product name, like Carmex. Second column, molecule, and you'd put phenol. And the last one, functional group, and I said alcohol, or if there's more than 1 functional group, you only have to name 1. Now, one of the things I did a couple years ago when students were losing points when they shouldn't is I put down the requirement that it must be a functional group we talked about in class, because functional groups we didn't talk about, students would always name wrong. I know these things because I'm an organic chemist. Now, it's time for a special gift from Dr. White. Email me before the deadline your project. I will check it. And if there's something wrong, I'll let you know on how to fix it. So you'll get a point for that entry. And therefore, if you take a little time, there's no reason why everybody shouldn't get 10. Yep, I still have 10 fingers, 10 bonus points. Plus, it's my sneaky way of having you look at ingredients saying, those are organic molecules, and they are. All right, any other questions about the extra credit project? If so, you can always come to my office hour or email me. Remember, before it's due, and try and do it, give me advance on that, email me your list and I'll check it. If there are things that are wrong, I'll help you correct it. So if there's no reason you shouldn't be able to get 10 bonus points. All right. Again, this is in the assignment area of Z2L, and it's visible to you. And I'll send out an email, not an announcement, because it's in the assignment area, reminding everybody about this the next day or two. We're in a class right now, you'd be watching me do this on a computer, which I just did. All right, we're talking about chirality. Chirality means handedness, and a chiral object is an object that has a non-superimposable mirror image, like your hands. You put it up to a mirror, forget about the ring, you'd see this hand and its reflection, and they're mirror images, but they're not superimposable. Notice my thumbs don't line up, only my center finger lines up. Everything else is off. If I go like this, it's about everything is off. So your hands are non-superimposable mirror image. They're chiral. Chiral means Greek, in the Greek language, handedness. And a couple of years ago, I actually had in one class, it was the summer Chem 170, 2 students who were fluent in the Greek language and said, yeah, that does mean chiral. Now, I was talking about chiral centers. I believe this is where I left off. Let me see. Yep. And what's a chiral center in this class? A chiral carbon. That's a molecule that has 4 different groups, tetrahedrally. Carbon with 4 different groups is always going to be in a tetrahedral structure bonded to it. So the question is, All right, let's look at A. The question is circle of chiral carbons. And those are carbons that has 4 different groups, 4 different atoms, or combination of 4 different groups and atoms. I think we did a couple of these last week, but let's go through it again. Remember, there's more than one atom, the same type of atom on a carbon. It can't be chiral. If there's more, if a carbon is in a double bond, triple bond, it can't be chiral. So your turn, circle of chiral carbons, 3 points each. All right, everybody's done, so I better get to work. And if a carbon has more than one of the same group, it's out. 3 hydrogens, it's out. 2 hydrogens, it's out. If it's in a double bond, it's out. If it's in a double bond, it's out. So that leaves this, and these carbons. And if we look at this one, hydrogen, bromine, methyl, and this whole long thing, 4 different groups. If we look at this carbon, hydrogen hydrox group, this I'll call R prime, there are 4 different groups. And finally, this carbon, chlorine, bromine, this I'll call R, and this I'll call R prime. They're different, so that's how you do it. Oh, let's do one more. All right, here's one more. Remember, every intersection of line right here, 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 and here are carbon atoms. All right, looks like everybody's done, so let's get to work. If a carbon has two or more of the same group or is in a double or triple bond, it can't be chiral. This carbon on top here is in a double bond. This carbon has two hydrogens, and this carbon has two hydrogens. So it's out. And what does that leave us? This carbon right here has hydroxyl hydrogen, R group, R prime, four different groups. Next carbon, hydrogen, hydroxyl, R and R prime, they're different, four different groups. And the last one, this one, same thing, hydrogen, hydroxyl, R and R prime, four different groups. And that's how you circle the chiral carbons. Now, switches off, but these are terms we use in organic chemistry, stereoisomerism. Those are isomers, molecules with the same number of atoms and the same type of atoms. They have the same molecular and structural formulas, but differ in their orientation of the atoms in space. Just like your hands are different in terms of orientation. I guess you could say your hands are pseudo-isomers, even though it's really used for molecules, not your hands. And isomers whose atoms are connected the same way, but different arrangements in space. Now, I didn't talk about it, but first of all, structural feature needed for isomerism, the presence of a chiral center, carbon. And it's got to have some sort of rigidity. Now, a special stereoisomer, click, switches on, are the enantiomers. And enantiomers are molecules with non-superimposable mirror images of each other. And if I look at the clock, I can give you an extra 30 seconds. Let's take a break now, come back at 1:50, and we'll continue on. I'll see you in 5. I'm going to go get up and stretch. time to get going. All right, I was talking about enantiomers. And what are enantiomers? A molecule with non-superimposable mirror images of each other. Now here we have glucose. You don't have to memorize the structure. Let's go to my whiteboard. And there we have, hold on, that's the awfulest looking G. That's better. Glucose. So how would you draw the enantiomer? Well, what's the enantiomer? It's a non-superimposable mirror image. Now, one of the things I've done, I don't know when I started doing this, I put in a mnemonic device to help me know what to do. And that dotted line is my mirror. Do you have to do this on a test? No. But think about it. If you hold your right hand up to a mirror, what are you going to see first? The palm, what's closest to the mirror. So let's do this. I'm going to have my backbone. Now, not achiral carbons, or not carbons that aren't chiral center, you don't have to worry about how you draw it because it's achiral. So the top one and the bottom one, I can just redraw like that. If you want to show the mirror image, you can, but you don't have to. But this one right here, here, and here, you do. So what's close to the mirror? Hydroxyl group. Well, you'll see that first in the reflection. What's farthest away? Hydrogen. Second one, hydroxyl group, farthest away, hydrogen. This one, hydrogen is closest to the mirror. You'll see that first. Hydroxyl group farthest away. Same thing here. Hydrogen, hydroxyl group, hydrogen. And here's your answer. Now, you might want to say, well, can't I just pick it up and rotate it? No. For Fisher structures, which is what these are, or projections, you can only pick it up and lay it over. You can't rotate it. Because just like a car has a top and bottom, same thing here. These are such that the stereochemistry, you can just pick it up and lay it over. You can't rotate it. So I better let you have some fun. And why don't you draw the enantiomer of this compound? In other words, draw its mirror image. Oh, I gave it away. All right, I think everybody's done. So how do you draw the enantiomer of B? Answer is draw its mirror image. And as you know, I like to put in my mirror. You don't have to. And up here, we have a carbonyl, which is a achiral carbon. So you don't have to worry about the mirror image. Same thing at the bottom. But if we look at this carbon right here, what's closest hydrogen, what's farthest away, hydroxyl group. Again, next one, hydroxyl group closest to the mirror. Therefore, you'll see that first, then hydrogen far away, and the last carbon that's chiral, hydroxyl group, hydrogen. So this would be the answer. That would be the enantiomer, non-superimposable mirror image of that molecule. Now, switches off for this slide, but it's a term I could have used, but I didn't want to talk about stereochemistry at the time. We can have stereoisomers whose molecules are not mirror image of each other. And these are called diastereomers. Remember, switches off, click for this slide. Example, two molecules, one cis, one trans. And they're not mirror images, but they are isomers, and we call those diastereomers. I'll never ask that on a test. Now, just to learn about it, this will not be on a test, but you may need to know this in other classes, and that is, all right, where did I put them? Hiding all the way over here. How do you do a Fisher projection? And I haven't mentioned it, but I should. One of the greatest of all organic chemists was a German chemist, Emil Fischer, Dr. Fischer. If you look on Wikipedia now, wow, great beard. That's Emil Fischer. And he died a long time ago in 1919. And he won a Nobel Prize. And he did a few things like Fischer esterification, but he's most known for his work in sugars. And they don't show it here, or at least I can't see it. Anyways, he's particularly noted for his work on sugars. He discovered a way of making derivatives of sugars to form molecules, which you could do crystalline, make crystalline, because not all sugars are crystalline, and identify the structure. Now, the sad part is to make that, he used phenylhydrazine, and that and some of the compounds he made, well, they were from sugars, and chemists back then would taste them. And guess what? He died of 2,4-dinitrophenylhydrazine poisoning. Lesson learned. Now, how do you do Fisher projection? This will not be on a test. If you notice, here's a three-dimensional molecule, carbon with A, E, C, and D. And if you rotate it like this towards you and flatten it out, you get the Fisher projection. Now, C and E are coming towards you. A and D are going back from you. But by flattening it out, it's easier to draw something that's really showing stereochemistry, location and space. Now, if we were to take this and call this silver, black, yellow, red, if I take this and rotate it, if I were to flatten it out, you'd have yellow on this side of Y, and R on this side. It'd be straightened up and down, silver on top, black on the bottom. And that's how you do a fissure, rotate it and flatten it. I'm not going to break my model. But anyways, I will not ask you to do that on a test, but at least you now know where it comes from. Now, when we talk about, in the next couple of slides, I'm going to turn the switch, click. Will this be on test to the off position? Why? Because this stuff you might need for other classes, but I won't put it on test. Now, when you have a monosaccharide like glucose or fructose, you have what's known as the DL designation. And that's based on the highest chiral carbon, whether the hydroxyl group is on the right or the left. Now remember, an aldehyde is 1, 2, 3, 4, 5. This is not a chiral carbon. So here's our highest chiral carbon. And notice the hydroxyl group is on the right, which uses dextrose, and L is, I believe, for levose, right and left in Latin. Even though Dr. White doesn't speak Latin, other languages, yes, not Latin. And therefore, when it's on the right, it's given a D designation, on the left, L. Now, this is D-glucose. And if we go to my favorite place, all right, what's going on here, sports fan? Huh. Wonder why it's coming up gray on my screen, but let's go to, it's weird. It must be having a problem. Or maybe I should have paid my bill. No. But anyways, if you see on your screen as D plus glucose, I'll be talking later today about, this is called the cyclic form of that. And that D tells you the hydroxyl group on the last carbon that's chiral is on the right side. Now, when we talk about enantiomers, molecules that are non-superimposable mirror images, this is something interesting. They have the same identical physical properties like melting point or boiling point or other things, except for two things. One is optical activity, and the other is reactivity with chiral molecules, other chiral molecules. And click, the switch is off, but this is important, especially for some of your other classes. So I do want to cover it, but I won't put it on a test or final of mine. What's optical activity? Well, when we talk about optical activity, optically active compounds are compounds that rotate plane polarized light. Again, switch is off. Now, what is plane polarized light? Well, the light you get from the sun, or my lights here, comes in waves, and the waves can be like this, like this, all the different degrees around the compass. How many of you ever seen Polaroid sunglasses? And those are the sunglasses that are really dark, and they filter off all the different ways except one, which cuts down a lot of the light. And therefore, they're good sunglasses. Well, turns out if I can make a filter so I can have this one wave of light at a certain angle coming at a sample. And if I measure how far does that wave rotate, I can find out, is that an optically active compound? Now, there are two ways it can rotate it. It can rotate it to the right or the left. Again, switches off for this slide. And things that are dextrorotary, right, rotate plane polarized light to the right, is given a plus sign. Things that rotate it to the left are given a minus sign. And if you notice this D-glucose here is D plus glucose. D tells you where that hydrox group is on the last chiral carbon, plus tells you it rotates plane polarized light to the right. This will never be on its S. Now, one interesting thing for plane polarized light, at a certain temperature and concentration, you put it through this plane polarized light, not only does it rotate it to the right or left, but at that temperature, if you have a pure sample, it always rotates at that degree of rotation. And that can be used to determine purity of certain sugars. All right, let's talk about monoclass, let me say that again, monosaccharides. Now, there's something called an aldose, and the switch is off here, but other classes may cover this, and you need to know what it is. And a monosaccharide contains an aldehyde, and that's called one that contains an aldehyde, a monoaldehyde, is an aldose, and glucose is an aldose. Remember up here, when we talked about it in chapter on ketones and aldehydes, I drew it this way, but I also mentioned you can write it this way. And these are both a way of designating aldehyde. And this is a monosaccharide, one polyhydroxyaldehyde that contains an aldehyde group, glucose. Now, if it contains a ketone, remember ketone, here I have carbons R, here I have carbons R, here I have my carbonyl. That's called a ketose. Anybody ever hear of ketosis? All right, you got to wait for 3 more rings. I'm going to drink some water. Stop. Thank you. All right. All right. Have you ever heard of ketosis? And that's a problem if you're diabetic, you have to worry about. That talks about your ketones, your monosaccharides. Now, about 3 or 4 years ago, I had, it was interesting, 2 diabetics in my class at the same time. How did I know that? Because they had just come out and they were wearing their insulin pumps on the patch on their arm. I wondered what the heck was that? And I said, could you explain that? And they told me what it was. I said, be careful in the lab. You don't want to get any chemicals on there. And that's a ketose, is a monosaccharide with a ketone. Now, a sugar is a designation for a mono and disaccharide. And here I'm going to turn the switch back on, click, because you should know what's a sugar. And that's a mono and disaccharide. So glucose and fructose are sugars. And also sucrose is a disaccharide. All right, switch is back on. And I'll talk about this in a second. But first, let's talk about D-glucose. D-glucose can exist in either form, and I'll explain that how it does in a little while. On the left is the acyclic, A not in a ring, cyclic, and B is the cyclic form on the right. Now, this is D-glucose, and I'll never ask you the structure, but I decide to tell you, it's the most abundant sugar in nature. And it's the sugar in your blood. And it's the aldohexose, which I'll never ask, and I'll never ask, but it just so happens it rotates plain polarized light to the right. One thing I should mention, there's no way any organic chemist can look at the structure of a molecule and tell you which way it rotates plain polarized light. You just got to go in the lab and measure it. All right, so this is D-glucose. Now, another sugar is D-fructose, and this is a ketose. And actually, it's called ketohexose, hexose coming from hex, hexane, 6 carbons. And it turns out this is the sweetest sugar available from Mother Nature. And a number of years ago, chemists helped food companies, or I guess corn oil companies or corn syrup companies, find a way to make high fructose corn syrup. And because it was cheaper than sucrose, table sugar, many of your food products now, if you look on there, like Coca-Cola or any other sweetened pop, has the high fructose corn syrup in it, because this stuff is super sweet, much stronger than table sugar, sucrose. And it's found, as I said, in corn syrup. All right, time for, do I have, oh, I do have time. Dr. White's story. I was working at this one company. I was a senior R&D manager. I had an idea. What if I could use fructose to make something that would be quite cheap starting material, and it would be a nice new product, and we could make some money. Well, I don't know what they're called today, but in, off way west on Harlem, off the Stevenson, company used to be called Corn Products. I don't know if they're still there, CP Corn Products Corporation, CPC. Let me take a look while I'm talking to you. I guess here's their new name, Ingredient, formerly CPC Corn Products that I knew them as, or CPC International. And they're located in that suburb, and they make high fructose corn syrup and also glucose syrup. So I called up the company, got into their marketing and sales, and what you don't know, but I'll teach you, any company that sells chemicals, any type, has what's called a sample room. And the sample room is responsible for sending out to customers or potential customers samples of their product. Those samples can be anywhere from 4 ounces up to 5 gallons. That's free. So I called them up, and I was a senior manager at this large multinational corporation, then called Borden Chemical Company. And I said, could you send me a sample of high fructose corn syrup? So I want to do some reactions with it, see if I might be able to make a product. Well, the salesman got all excited, not on the phone with me, but obviously with his marketing manager. They approved, and I only needed about 4 ounces. They sent me 4, yes, 4 5-gallon buckets of corn syrup. The sad thing was it wasn't food grade. Because if it was food grade, I could give it away to people in my research group. Because we only needed an ounce or two. Turned out it didn't work what I was trying to do. But so now we had essentially 20 gallons of industrial grade, non-food grade, high fructose corn syrup, which is pretty thick, like molasses almost. And we were located on a site with our plant for our company. And I had my people bring it down and tell the plant manager, because that was standard, it's not hazardous, get rid of it. And he wasn't too happy with me. I took him out to lunch to apologize, but I didn't ask for the 20 gallons. And this can exist also in a cyclic form. Now, this form right up here, the cyclic form, and see how you have the different darker lines. And up here also, this is called the Hawthorne projection. It's a way of showing three-dimensional structure, ring structure of mono and disaccharides, and also other lot bigger carbohydrates. And this will not be on test. It even says it on the slide, but I thought I'd just point it out. All right. Now, before I go into this one, I have to little bit break my promise to you. Well, at this point, I don't have to. I'm sorry, I got ahead of myself. All right, let's take a look at this reaction here. You see on there, on the left is glucose in its acyclic form. And there's an equilibrium to the cyclic form. Now, what's happening? Well, this is very important, because if this reaction didn't happen, we would not have any of the starches or the carbohydrates that you know and love, like potato chips, French fries, mashed potato, all the good stuff in life. That wouldn't exist either with trees, grass, or any other. All right, let's take a look at the following reaction that you learned a long time ago. If you take a ketone or aldehyde, react it with an alcohol, the presence of an acid, keep your eye on the carbonyl carbon, what was attached to it, our primer hydrogen or our double prime is still attached to that carbon. You'll have the alcohol OR prime to make this, and this will be a hydroxyl group. And this we learned is either a hemiacetal or hemiketal. Time for Dr. White to be subtle. Hint, know this. All right, let's look at glucose. This is the time in a semester. You have to be patient because it takes a little while to draw these. here we have glucose. Now, notice I have an aldehyde on the top. And at C5, carbon number 5, 1, 2, 3, 4, 5, I have a hydroxyl group on a carbon and alcohol. So, and let me write it again up here. Now, this alcohol is this. This carbonyl is this carbonyl. And what happens is this hydroxyl group attacks that, just like this hydroxyl group attacks that. And because it's in the same molecule, that's called an intramolecular reaction, you don't need a catalyst. Now, do you break carbon-carbon single bonds? No. So first of all, this is still going to be here. Anything that's not involved in the reaction will still be there. Now, this oxygen is this oxygen from the OR, and it's bonded to the carbon that was the carbonyl carbon. So I could either have you spend the next 2 weeks trying to master Hawthorne structures and not succeed. I tried that the first time I was teaching this class, and none of the students mastered it. So I came up with a better way, and that's the world's longest and ugliest carbon-oxygen single bond. And this carbon right here is this carbon right there, and we'll also have a hydroxyl group. And this is a cyclic form of glucose. And that's how you do it. Let's talk about this again, because notice, hint, you should know how to do this on a test. If I give you glucose and the double arrows and say give the product or products, you should know how to do that. If I give you the product and the double arrows, what's the starting material? All right, here's glucose. We have an aldehyde on top, alcohol at carbon 5. Just like this alcohol attacks this carbonyl, this alcohol attacks this carbonyl. And between this oxygen, you form a bond here, which is this bond right there. And it also has an OH group on there. And that's how you do it. Now, this is the same thing. This carbon right here is this carbon right here. This oxygen comes from here. Now, which is easier to do, my way or learn how to draw this? How many of you would rather do my way? Give me a thumbs up. And it is easier. Thank you. And that's my way of helping you succeed in this class, because it's just easier for the students. So let's go through this again. If this reaction didn't happen, we would not have any of the complex carbohydrates, starches, or cell walls of plants and trees that we have in our world. And therefore, what is it? In this case, an aldehyde reacting with an alcohol. Now, since it's intramolecular in the same molecule, you don't need an acid catalyst. If we're intermolecular, intermolecular is outside, like if you're going to go on an international flight, you're going to leave the country. Well, that means like the reaction I have up here with the acid catalyst, two separate molecules, then it helps to have a acid catalyst to make it go quicker. And this alcohol reacts by attacking the carbonyl, just like this attacks it right here, and forms the hemiacetal. Well, here, right here, it's the same thing. And this is a real bond between this oxygen and this carbon. Students tend to forget about that, or the other thing is forget this hydroxyl group on there. And that you should know how to do. Now here is fructose. And let's draw it. Let me remember what it is, because if you haven't guessed, I've never worked industrially or even in academics with these sugars other than at one time. All right, this is fructose. And it's a sugar, the sweetest one known. And excuse me, let me remind you. Did it again. Ouch. You learned this for test number 2. So here's my carbonyl for the ketone right up here. And again, carbon 1, 2, 3, 4, 5. At C5, this alcohol will attack that carbonyl ketone. Oops, made a mistake. No, it's right. Let's do this. No, I didn't make a mistake. What's not involved stays the same. This hydroxyl group is now this oxygen, which is bonded to what was the carbonyl carbon, this right here. And also on that, you'll see a hydroxyl group. And this is a cyclic form of glucose. And I'm missing something here. And once again, we have this attacking here to form the hemiacetal or hemiketal. In this case, hemiketal. Same thing here, attacks this carbonyl to form this. Oops, I forgot something. Quick, don't look. There, the oxygen fell off. If you see it, let me know where it went. Oh, that was awful, Joe. And forms this. And you should know how to do this. And if that didn't happen, we wouldn't have sucrose, table sugar. And that's how you get the cyclic form. Which is easier to draw? The Hawthorne structure, where it says beta D fructofuranose, or Dr. White's make it easy for the student structure. I hope you all think Dr. White's make it easy for the student structure. You should know how to do these. And here I showed how to form the hemiacetal or ketal form of a monosaccharide for glucose and fructose. Now, reduction, C board. Oh, I got to get to work. If you have a ketone or aldehyde reacting with hydrogen and catalyst, you'll form an alcohol. Break the pi bond, not the sigma bond, and form this alcohol. Since I've been having all the fun, why don't you do this reaction? What would be the product or product reacting a glucose with hydrogen and a catalyst? By the way, alcohols will not react with hydrogen and a catalyst. Oh, excuse me. All right, everybody's done. Let's take a look at this. Oh, look what's different. At the top here, we have an aldehyde. Aldehyde or ketone, hydrogen catalyst, break the pi bond, each atom gets a hydrogen. So do you break carbon-carbon single bonds? No. So all this at the bottom stays the same. And this opens up to an alcohol. And if you notice in this new molecule here that we just made, each carbon has a hydroxyl group on it. And this has a special common name, sorbitol. How it got that name, I don't know, but let's take a look at sorbitol. Now here they're showing stereochemistry, but if you notice there's 6 carbons, each bend in a line is a carbon, and each one has a hydroxyl group on it. And this is sorbitol. And how do you make sorbitol? You take glucose and reduce it. Reduce it means you add hydrogen and catalyst. So you take the most abundant sugar in nature, glucose, and you react it with hydrogen catalyst, and you get sorbitol. Now, sorbitol is used in a sweetener in special cases. And where's that special case? It's in over-the-counter medicine. If you buy cough syrup or other things like that, they put sorbitol in there to make it taste sweet, and it does. And that's reduction, but that's the most widely reduced sugar to make sorbitol. Now, don't copy this slide down yet, or even actual, but I'm going to go through this, and this is called glucoside formation from monosaccharides. And a glucoside is the acetal or ketal form of a monosaccharide. If I look at the clock, it's time to take a break. We'll come back in 5 minutes. I'm going to do some more stretching, and we'll continue on into the wonderful world of carbohydrates. Let's get started. All right, now, earlier I said no new reactions. Well, this is sort of not new, but sort of is. And let's talk about the following. For test number 2, you learn the following reaction. Have a ketone or aldehyde. What's attached to the carbonyl carbon will still be there. And on that carbonyl carbon, when you react it with not one, but 2 alcohols, you'll get this hemiacetal or hemiketal. So when we look at this, we say, okay, that's what happens. What I didn't show you is how this goes stepwise. This won't be on a test. Now you learned again for test number 2, I'm sorry, that if I take an alcohol, react it with a ketone or aldehyde and ask the catalyst, I'll make the hemiacetal. And that's this right here. I'll call this A. And then the second alcohol replaces this hydroxyl group with the second OR. Now, what I didn't teach you, hold on. I'm getting all choked up over this stuff. That was awful, sorry. But anyways, what I didn't teach you is where this top route to go to this compound, I'll call B, is a symmetrical addition. Both R groups on the oxygens are the same. Well, it turns out you can have unsymmetrical formation by taking the hemiacetal A or ketal and reacting it with a different alcohol. This A you can isolate. What's attached to it. And the hydroxyl group is replaced with OR. In this case, the R is triple prime. So the oxygen alkyl groups are different. And this is unsymmetrical addition. And this is what we're going to do. And that's this reaction right here. And let me show you how this goes. So technically, well, I could say this is not really a new reaction, but really it sort of is. So I broke my promise just on one reaction. And now if we take our hemiacetal or hemiketal reactor with a mole of a different alcohol, ask the catalyst, you'll replace this with this. Everything else on that carbon stays the same. Well, the question is, so what? Well, let's take a look at this. By the way, the closer it gets to May, the worse my hydrogens look on a sugar molecule. Not really, but today it looks that way. And here we have the cyclic form of glucose, called, I think, a glucoside. And if I react this with any alcohol plus acid catalyst, what happens? Well, guess what? I'm going to let you try this because I've been stealing all the fun. What would be the product or products of that reaction? Hint, look above, top of the page. I should point out this reaction, I'll never give a synthesis problem. That's not fair. All right, let's take a look at this. What's different? Well, we got all these hydroxyl groups in this oxygen, but if we look at this carbon right here, it's got a hydroxyl group, hydrogen, oxygen, bond to this. It's this right here, but our up here in our, we could call it double prime, are connected together in the ring. And therefore, the only thing that changes this changes to this. So if that's the case, that's this hydroxyl group. Everything else stays the same. And the only thing that changes is this becomes this. And this turns out to be very important. But let's take this for a ride with the real molecules. Your turn. What would be the product or products of the following reaction? While you're doing that, I want to look up something real quick. Nope, doesn't have it. All right, let's take a look at this. What do we have here? Well, a lot of alcohols, but we have a hemiacetal. And we're reacting this with an alcohol, an acid catalyst. And you replace this hydroxyl group. Everything else stays the same with this. Well, what's our triple prime? Ethyl. So, other than that, nothing else changes. And this OH becomes OR triple prime. What's my R triple prime? Ethyl. And that's how you do it. Now, one of the questions you should be asking me always is, why am I learning this stuff? What good is it? And that's a good question. So let's find out. All right, what I'm about to write on the whiteboard, do not copy down. Trust me, you can always come back to the video, but you don't need to copy this down. It'll take me a while to get all these written, so go read a good book or something while I'm doing this. And if we're in a classroom, you'd be watching me make the same mistake I just did, pick up an eraser. Hang in there. 2 days later, I'll be finished. All right, let's take a look at, let's call this A, B, C, and D. Is that original or what? Don't answer that. A can react with B with an acid catalyst. How? We have the hemiacetal or ketal reacted with an alcohol. Will form the acetal or ketal. Now, here, right up here, I have this. And right here on this carbon, I have my alcohol. So this will bond to that carbon. You lose this, and you'll form a bond between A and B. Now, if you look at B, we have, oops, that's not what I want to do. We have this carbon, again, is this carbon, and this hydroxyl group is this alcohol. And guess what happens? I lose the hydroxyl group. And that gets bonded together. And that's this bond right here. Now, if I look at C, it can react with D to do the same thing. That same alcohol can react and form a bond between itself and that carbon. Again, forming this bond. And notice I've linked glucose molecules together in a polymer. And guess what? I could keep on doing this more and more, like the Energizer Bunny. Now, if I wanted to show it shorthand, I could have said this. And if you link about 50 of these glucose molecules together this way, we have a molecule you're familiar with, starch. That's how we also make the cell walls for plants and trees. I guess trees are plants, aren't they? I guess. I don't know. I'm not a botanist, so I've learned the lesson, don't be an expert in an area you know nothing about. Just because you, oh, famous life lesson. I learned this early on in my life from a good mentor. Just because you're extremely educated, knowledgeable in one area, doesn't mean you know all areas. I have a PhD in organic chemistry, and I know it quite well. But when it comes to medicine, well, I know some basics. What do you do when you get sick and things like that? But am I an expert? No. Therefore, don't try to be an expert in all areas. So if we look here, what we've done is link glucose molecules together. And when you link enough of them together, you form starches, which is the foundation for our food, a good part of our food. You know, there are the 5 food groups: starches, fats and oils, or carbohydrates, fats and oils, proteins, beer, and pizza, you know, the 5 major beer, food groups. But anyways, that's how Mother Nature uses this reaction to link glucose molecules together to make starch. And the glucose side is the cyclic form, and that reacts with itself. Uh-oh, I ran out of memory. Hang on. Let me. Nope, I gotta shut down the old-fashioned way. Well, anyways, you saw what I did. I lost it. And therefore, you form glucose. Hold on. I keep on forgetting to do the following. Starches are just glucose molecules linked together in acetal formation. And that's what a starch is. So if I were to ask you the following 3 points each, give the structure or write the name of the following reaction product. If I react a lot of glucose molecules together with acid, what do you get? And the answer is starch. Or cellulose in plants. And that's this glucose linked together. So you should know that glucose molecules are linked together by an acetal linkage to form starch. And that's why I have down there, remember the reaction with methanol and the alcohol. I used ethanol today. Now, an interesting thing, and I'm going to turn the structure of this off, but I will ask you to learn the following. Sucrose, table sugar. What is it? It's an acetal between fructose and glucose, and they're bond together. This is a cyclic form of glucose, and it's in the Hawthorne projection, and this is the cyclic form of fructose. And it forms the structure. And what you should know sucrose is a glucose and fructose molecule linked together. And I should get subtle. All right. I didn't spell it right. There, now it's spelled right. You should know sucrose is a glucose and fructose molecule held together. Now, when you link a lot of glucose molecules, monosaccharides together, and it's called a glycosidic linkage, which I'll never ask on a test, the acetal or ketal form, we form polysaccharides, otherwise known as starches. So remember how I said how a lot of people say, oh, I hate organic chemistry? Well, if you do, you wouldn't have the food around you to keep you alive. And therefore, that always makes me chuckle when I hear that little laugh. Again, starches are polysaccharides or polymers of glucose. Now, it switches off for part of the slide, and that is amylose is when you have the hydroxyl group on carbon 4 reacting with the hemiacetal at the top on carbon 1. Now, this switches off. You can also have branch starches, and we call those one type amylopectin. There where you have both 1,4 and the hydroxyl group on carbon 6 all the way at the bottom reacting, just like I just showed you. Now, let's talk about another reaction you learned. If you take a acetal or ketal, react it with acid and water, what happens? If you take that, you get back the aldehyde or ketone you would have used to make that acetal or ketal, plus the alcohol you would have used. And if you had to, you could write a 2 there, but you don't have to. Now, in the case where one of these is unsymmetrical, you'll get 2 different alcohols back, OR and OR triple prime. Well, what does that mean? And this is something that goes on in your stomach. Uh, Now here, what I have are two glucose molecules bonded together. And right here, that's a hemiacetal or acetal linkage. So the question is, what happens when I react this with acid and water? Well, here you'll get back glucose. I'll get two of them. This breaks just like now. Here I have how we learned for chapter 2. Now this carbon right here is this carbon. And here this oxygen is this oxygen. And this one is the other. And what you get back is the aldehyde ketone. And one of these alcohols is bonded to that, or it could be in the cyclic form. So what I'd get back here are two, when I break that, cyclic form or the acyclic form, either way. Is this. So what does this mean? Leaving my class, I would like you to understand what happens when you eat a carbohydrate. And what I like you to know this. How do you describe with words in a general reaction what happens when you eat a carbohydrate? And the first thing is, that's acid hydrolysis of an acetal. And for test 2, the general reaction for both an acetal and ketal, you take the acetal or ketal, acid and water, see what happens after a holiday weekend. I get sloppy. By the way, I hope you all who celebrated Easter had a happy Easter and got all the eggs and chocolate bunnies your hearts desired. For those of you who celebrate Passover, I hope you had all the matzah and wine your heart desired. For those of you who celebrate neither, I hope you had a nice weekend. All right. Keep your eye on the carbon with 2 oxygens. You get back the ketone or aldehyde, plus the alcohol you would have used to make that. In this case, they're connected together to make glucose. So the question is, how do you describe with words and a general reaction what happens when you eat a carbohydrate? Words: acid hydrolysis of an acetal, general reaction, acetal and ketal, acid and water. You get back the aldehyde and ketone you would have used and the alcohol you would have used to make that acetal or ketal. So you should know this. Now, one of the things I now remember, oh no, I neglected. Well, not really. I didn't want to confuse you, test 3 and 4, but now I can also talk about what happens in your stomach when you eat something with a fat or oil in it. Say if you had a hot dog for lunch or dinner or breakfast, or if you had butter on toast, how do you describe that? With both a general reaction and with words. Well, what's the functional group in a fat or oil? An ester. And what happens in your stomach when you eat a fat or oil? You have acid hydrolysis of an ester. And what's the general reaction you should know? For test 3, you learn ester, acid, and water. You get back the carboxylic acid plus the alcohol you would have used to make that ester. In this case, fatty acids plus glycerin. And you should know this. So let's go through it again. How do you describe with words and a general reaction what happens in your stomach when you eat a carbohydrate? Well, the key functional group holding glucose together is the acetal linkage. And therefore, you have acid hydrolysis. Remember the important thing in your stomach, water, and hold on while I drink some. And I always think it's one of the miracles of life. You and I both have, or all of us have, cells in our body that manufacture synthesized hydrochloric acid. That just astounds me, but I'm a chemist. And acid and water, acid hydrolysis of an acetal. Here's the general reaction. Acetal, acid and water, get back the ketone or aldehyde plus the alcohol you would have used to make that acetal or ketal. Now, fat or oil, what happens in your stomach? How do you describe it with words and a general reaction when you eat something with fat or oil in there? If you had an oil vinaigrette dressing, if you had French fries or potato chips, which unfortunately my doctor always reminds me you shouldn't be eating those. I've had French fries and I bet a good 8 or 9 months because I stay away from those. Same thing with potato chips. Oh, is that sad? But anyways, I'd rather be alive and stay away from it than not. Anyways, what's the key functional group in a fat or oil? And that is an ester. And therefore, what happens? You have acid and water in your stomach, you have acid hydrolysis of an ester. And that reaction is right here, ester, acid, and water. You get back the carboxylic acid plus the alcohol you would have used to make that ester. Now, let's look at the following. While we're talking about digestion and eating things, sucrose is what? A glucose molecule bonded by an acetal linkage to fructose molecule. With that knowledge, if I were to do the following, take glucose and fructose with a little acid. And by the way, acid catalysts, what do we call those in our body? Enzymes. Most of, not all of the enzymes are very fancy acid catalysts, providing a form of H+. If you react glucose and fructose together, what do you get? You get sucrose. Now, what happens what would be the product or products of taking sucrose and consuming it in your stomach with acid and water? I'll let you try this one. And the answer is glucose and fructose. And if you come back up here, remember when you take a starch and react it, I don't know, I'll write it down again here. And you should know this. You get glucose. I'm not balancing the reaction. So starch will give you a glucose. And why is that the most abundant sugar in nature? Because both your body and animals' bodies break down the starch when they digest it to make glucose. And if you have table sugar in something, you break it down to glucose and fructose. Now, how many of you have heard, it's been around for a number of years, where there have been certain mothers groups that were concerned about illnesses their children have. And some of them have decided that having high fructose corn syrup, which is only in the last 40 years in our food chain, mainly for children, or a lot for children, has caused serious medical difficulties. Now, they believe it caused things like autism and other things, and they've gone after the food companies to lower the fructose. And some of them said, oh, we've heard your pain. Guess what? We'll do that. So what do? They replace some of the fructose with sucrose, table sugar, how it used to be. And they went to the mothers groups and say, see, we're replacing that. And what I say to that, and this is my personal opinion, that's not the right thing. The right thing is the fact that the high sugar level, whether it comes from fructose or sucrose, is bad because it causes you to be overweight. And that's not good for your health. Luckily, I work out, walk a lot, but still, it's not good for your health. So what does that mean? When those food companies replace the fructose with sucrose? Well, what it means is when you eat sucrose in your stomach, you're making fructose and glucose. And we've been doing that for eons. And I don't think that high level of fructose is causing the medical problems, other than it's a lot of calories, whether you get it from table sugar or high fructose corn syrup. But that's my own personal opinion, and I'll label it as such. Now, if you look up above, you have cellulose, and underneath you have starch. And the big difference is between the two, and this is the cyclic form of glucose. In cellulose, the stereochemistry, the oxygen bond that I showed you going like this, part of it's above the ring and part of it's below. There's a name for that, and I'm not a carbohydrate chemist, I forgot it. And in starch, the oxygens are both below the ring. And that makes a difference in the chemistry of how quick, it's called the reaction speed or rate, hydrolysis happens, acid and water, to make glucose. Now, in starch, it's pretty quick. So you and I can eat something with starch and our body can break it down. Where do you find cellulose? Plant material like hay, grass, or even the paper you're writing on. And if you were to eat those, would that keep you alive? No. However, horses and cows and elephants can eat it. Other animals, what's the difference? Well, a horse has a huge stomach, and the residence time of the cellulose, say grass or hay, that remains in their stomach is long. If we were to eat it, because we have tiny stomachs compared to a horse or a elephant or a cow who's got 4 stomachs, it wouldn't last long enough in our stomach to be digested, broken down. And that's an important thing. And if I look at the clock, oh no, we're almost out of time. All right, listen up. Tonight from 5 to 6:15, I'll have my office hour. If you need any help, stop by. I'm going to send out an email. I won't do it as an announcement, just an email to remind you to look at the assignment area of D2L for the extra credit project. Remember, 10 bonus points. And remember, I am going to offer a special public service. Shh, don't tell anybody I'm being nice, but I am, that if you email me your project before it's due, I'll look at it and say, oh, this is wrong, and get back to you on what you got to change or find a new molecule. Remember, it has to be organic molecules with functional groups that we've done in our class. And with that, I'm going to say, Gang gesund, goodbye. I'll see you either tonight in my office hour or Wednesday. Have a nice couple of days until I see you again. Gang
Thank
gesund.
you.
You're welcome. Bye.
Bye.
Thank you.
Bye.